Everybody ready? So this is the long-awaited brain dump of the training that Rackspace was so generous to send Hi Ty and I on back in July. We spent a week with DataStax. Some of their top developers and engineers were actually there, also as students and half as TAs. We had a little bit of fun in DuPont Circle. Some of us may have had a little bit too much fun, but people back home also still had fun. Never send an email to SMTP dev. So anyways, we're going to start off with some basic foundational ideas. First, we're going to talk about some of the correlations between what you already know in MySQL, I'm sure, and what Cassandra has as a vague, rough equivalent. None of these are exact analogies. It's just like for a mindset. So in MySQL, you have databases. In Cassandra, you have a Keyspace. And in MySQL, you have a table. Cassandra has column families because Cassandra is a column-oriented database system. In MySQL, you have your primary key, which is what you would use to index and access all of your data fast and efficiently. In Cassandra, that is called a row key, but it's the same general concept. And then as far as query languages, it's technically Cassandra is a NoSQL engine, but I hate using that word, and I promised myself I wouldn't say that. But you have a query language in Cassandra called the Cassandra query language, CQL, which I won't really tell you anything about. Ask a developer. As I said, Cassandra is a column-oriented database, so everything that you store in it is going to have key value pairs. So you have a row key, which is, think of that as the key for your entire row, your entire collection of columns. And then within that row, you have all sorts of other columns. They do not have to be uniform. There's a very loose schema. Data types aren't even examined until after you've already written your data and you decide you want to access it now and create a loose definition of a schema around what you probably have in your key space. So you can insert into a new row whatever you want. You can call it whatever key and value you want. You can also, your value on a value tied to a column name can also be another row or another column or list of columns or whatever. So you can that's how you can have sub-columns and like dictionaries inside of a single value. Everything in here, we're going to talk more about this later, but every single value in Cassandra is also time-stamped. So those numbers that you see in the third row of each of those key value pairs, that is an approximation of a timestamp in microseconds from when that value was created. So every single thing that happens is timestamped in Cassandra. That becomes very important later. If for the computer science-y types out there, you'll be familiar with the CAP theorem, which says that you have a triangle of consistency, availability, and partition tolerance, and any database system can only pick two of these. And if you pick two, you're going to be fundamentally bad at the third. So Cassandra picks availability and partition tolerance, but I'm going to be stressing this multiple times. Cassandra picks consistency and availability and partition tolerance. So it promises to always be available, and it promises to always have some reasonable thing to do if different parts of the system or the cluster fail. That isn't necessarily, though, to mean that it's not consistent. There are other systems that claim to not be consistent, like CouchDB, which are less consistent and are just fundamentally stuck with that. Cassandra has a lot of tunables and a lot of things that you can do as you're designing your access patterns to it that allow you to still maintain consistency to a level that you need for your application. Also, another fundamental tenet of Cassandra is that you need to think about your data differently. Everybody that has ever been through a database class has heard about normalization, and you've heard about taking your data set and forcing it into different categories that we call tables and making references between all these different tables, and you're taught to think that it's bad and dirty to have multiple copies of the same little atom of data across multiple tables or across multiple places in your system. That you just need to forget that. Storage is cheap. Cassandra is designed to be ran on cheap hardware with cheap hard drives and cheap CPUs and cheap memory. And so you need to be able to think about how you're going to access your data, reading and writing it, and then put it in more than one place if necessary, into places that's going to be quick and easy to access. So you have to, as you're designing your database structure, you start with your application and what it's going to be doing, and you design your structure around what your application does to it. And that also might mean that in the future, as your application changes, the structure of what you're writing changes. So yes, your application is going to be writing data into multiple places. You're going to already be using some sort of a sophisticated Cassandra driver in your application to talk to the Cassandra cluster in an efficient way. And it's already going to provide you abstractions to make that easier too. So, and even if it didn't, even if you're using some sort of simple little thrift thing that talks to a single Cassandra node, it's still simple enough to say, here's a function to update the name of a user, and it just goes through and updates it in all the different places that it needs to go. Code is also simple, especially since I'm talking to a bunch of developers. So your, this chart, I guess, is just showing you the difference between a model that you would have in a relational database system where you have tweets and users and followers, and then you have this table of associations. And in a Cassandra design, you would have, I need to find all the followers, and so here's all the data that I need to do that in one table. And if you need to look at the tweets, here's all the data that you need for that in one table. So you don't have to look up 2 queries to the users table and the tweets table just to get the name of the user. So a Cassandra cluster is going to be thought of as a ring. So just get this picture stuck in your head, and we're going to have different modifications of this as we continue to talk about different things that you do with it. That ring has every node in there is effectively analogous. Like they're all doing the same things. There's no one special node. There's no master. There's nothing like that. But there are different roles in different operations. So a client would connect to one of these nodes, and that node that the client is connected to is referred to as the coordinator, because it's going to be coordinating everything that the client needs to do. All these nodes are going to be talking to each other with a protocol called the gossip protocol. So we'll be talking about how gossip handles this and that and informs nodes of other things. It isn't exactly a mesh topology, so like you don't necessarily gossip with all nodes, but all nodes do need to be able to talk to each other because it may at some point decide it wants to talk to a similar node. There's also a idea of topology in your Cassandra configuration. So it's not just nodes holding your data, it's nodes that sit inside of a rack, and then there's a bunch of racks that sit inside of a data center. And that entire topology of all these different multiple data centers makes up your entire cluster. So things like replication and repairs and consistency and stuff like that can all be aware of your position of a node within a rack or a data center or anything like that. This is also a good reason to use a good Cassandra driver in your application. So DataStax, the commercial enterprise force behind Cassandra, writes some really good drivers for a lot of different languages. Their, I guess, top line driver is the one in Java, of course, but the DataStax driver for whatever language you're working in is going to be the most aware and the most sophisticated at knowing where your client is, where it needs to talk to, and being able to handle all sorts of different failure scenarios. That gossip protocol also includes information about the load, the response time, the current position of that node within that ring, stuff like that. speaking of position on the ring, Cassandra has sort of like an inherent ability to shard, and sharding is like a dirty and bad thing to do efficiently because it always causes all sorts of other problems, but Cassandra seems to do it pretty good. You define a token, and you assign that token to a node. And that token is just a number which associates it to a position along this ring. Every single primary key, or every single row key that comes into a cluster for a read or a write or whatever, it takes that row key and it hashes it, and then that hash is another position on this ring. So if you have the hash of key 1 there, it points to that red area, and that means that it will find that point on the ring, follow it clockwise, and then it will apply that operation to the first node it hits. So in this simple example, your token is essentially, I'll handle all the things, all the values for your entire spectrum of data up until my token number. That also, as you can see in here, it's not necessarily evenly distributed. You don't have to be even. You usually want to be, though. Replication is handled by essentially just making, you write your first copy, the authoritative copy, or whatever you want to think of it as, to that first node that you found on the ring, and then you just walk the ring for however many more nodes that you want to make copies of that data. So if you have a replication factor of 3, meaning that there's going to be always 3 copies of your data, then it will write it to the first node it sees plus the next 2. If your topology and your replication strategy is aware of racks within a data center, then it will write it to that first node it found, and then instead of just blindly writing it to the very next node on the ring, it will keep walking the ring until it finds a node in a different rack, and then it will write the next copy there. So I don't have a good diagram of this, but if you can imagine, let's say you have the first 3 nodes in one rack and the next 3 nodes in another rack, that means that every single write that goes to any of those first nodes on the first rack, its next rack replica or whatever is always going to be the first node in that second rack, which creates an incredibly high hotspot. So that means that that first node in your second rack is going to take half of all of your writes. So that's a hotspot for I/O operations of both disk and network. It's a hotspot for processing, for handling all those updates and all the compactions that we'll talk about later too. That normally means that either some people just decide they don't care about racks and they'll just handle consistency and replication, not caring about what rack it's in. You know, if you lose half your cluster, Cassandra is still fault tolerant enough that it can still handle that if you have everything else designed right. Or you'll just alternate racks in your ring. So you'll have rack 1, rack 2, rack 1, rack 2. You also are encouraged to not just use simple tokens on your ring. So that means that it's simple to think about having a 1/3 of your pie of that ring be assigned to a single node, but operationally that's difficult to manage. It's a lot easier to say that here are a whole bunch of tiny little partitions. A partition is a space between 2 keys, and we're going to assign this whole list of tiny partitions to this one node, and then this other list to another node. And then you take those partitions and you shuffle them all around so that each node has a bunch of partitions all across the ring. That makes it also a lot easier to add and remove nodes, because in this smaller example, if you were to add a node between 2 and 3 there, then it would, the onus of loading that new node with new data would be all on node 2, because it's going to be taking up node 2's key space. If you have the key space distributed across your entire cluster, then all the nodes can participate in provisioning that new one. It also means that if a node goes down, the read operations for that downed node don't all go to the same next one. It's also a lot easier to manage hotspots of like replica hotspots if you're using a rack-aware topology and stuff like that. If you have them distributed like this. So, okay. The internal architecture of how Cassandra works. We're going to go through the read and write path of how data is read and written to a Cassandra cluster, both between different nodes and within a single node itself, and then also some different mechanisms and functions that occur within Cassandra. So first, we're looking at the write path of our single write operation to the entire cluster as a whole. So the client connects to N9 there, the node 9, and that node 9 is now the coordinator for that client for this operation. 9 looks at the write operation, looks at the replication factor of that key space that the administrator has configured. It looks at the consistency level being requested by the client, because the client can say, I want to write this and make it this level of consistent. And it has decided that it needs to write to both of its local replicas in the same data center, so that's node 2 and 3 above it. And then it also needs to write a single copy to one node in each of the other data centers. So that's, and the way it does that is not by directly connecting to whatever public IP or whatever you have those remote nodes on. It will connect to a single node that it will pick based on utilization and load and stuff like that in the remote data center, and then that remote node, in this case node 1 and 5, will become remote coordinators. So it's as if node 9 is a client again, and 1 and 5 are coordinators for that client connection. And so then 1 and 5 will then talk to the nodes that update needs to happen on. Does that all make sense so far? Yeah. Okay, cool. So you'll also see there that node 9 wants to write a copy to its local node 3, but that, for whatever reason, it can't talk to node 3 because it's down or there's a network partition or whatever. So what 9 is going to do is it's going to save what's called a hinted handoff to its own disk, to its own state. So it's just a little notation in its system key space that says, I have a write for node 3, and I can't do it right now. But as soon as I'm aware of node 3 being up again via the gossip protocol, then I'm going to go ahead and send that to node 3 saying, hey, while you were down, you missed this. Also, what is happening within each given node is an update to several different Cassandra internal data structures. So this was the best picture I was able to find, and I'm sorry that it includes a lot of things that aren't relevant to what we're talking about at this moment, and I'll show you this again when we're talking about the read path. But what this is that when an update is happening, which is the black arrows at the top left there, that update is written to 2 places. It's written to the mem table, which is a in-memory data structure of all of its most recent current updates, which internally has a buffer and of the indexes and the data. And then it's also written to a commit log. The commit log is just that. It's very analogous to the MySQL bin log, where you just have a list of updates that have happened in order. Whenever a node goes down, the commit log is used to figure out what was going on at that time to regain a consistent state. And then at that point, once it's flushed to the commit log, which the commit log itself is on disk, then that write is considered done. Asynchronously and in the background, there's all sorts of things that will move that data around. So it's not just going to stay in the commit log forever. When that commit log either becomes full or when some time expiration has reached or whatever, there's a lot of configurable components in there, then that commit log will be turned into SSH table. Well, no, it's not. It's not that. Specifically, it's the mem table that's turned into an SSH table, but same idea. So that also, the commit log, the sync to disk part, that can also be something else that the client can configure and say, I don't really care how fast you write this to disk, just record it in your mem table or whatever for all I care, and then return back to me that the write was a success. So the SS tables, it stands for a sorted string. It is the fundamental on-disk data structure that embodies your data. You will have multiple SSS tables, and there's strategies for compacting them that we'll talk about later. But within an SS table, you have multiple indexes that allow you to find your data within that SS table and find which SS table your data is in really quickly. So you have a row key, which is a part of your data, and you also have a hash, a data structure in memory that says, here's my row key, and it is most likely on this list of SS tables. And you can also then take, if it's not in, sorry, I'm getting different data structures confused. When you write to, we'll talk about more about this in the read path, but when you write to an SS table, the main bits that are updated is that there's a Bloom filter, which gives you like a probabilistic indication of where your data is. So that's a smaller in-memory data structure. And there's also all sorts of various caches and indexes that say this row is in this table or is in this list of tables and stuff like that. A delete is, because SS tables are immutable and your commit log is also immutable, there isn't actually, deletes don't actually delete data. Instead, a delete is actually just another special update called a tombstone, which says this row key no longer exists. So tombstones are cleaned up in the compaction process that we'll talk about later, but what it essentially means is that as Cassandra is reading through the most up-to-date update for a given row, if it's a tombstone, then that row doesn't exist anymore. So it may find 5 old copies of your row plus a tombstone, and if the tombstone's newest, then your row doesn't exist. Okay, so your read path. Same as with a write, your client connection will go into whatever first node the client connects to. It will be your coordinator. Your client will say, I want this level of consistency when I am talking for my read operation. You can also configure other options like eager retries, for example. So if you're, you have a replication factor of 3, so there's 3 copies of your data somewhere in your topology. The coordinator will, through the gossip protocol, know which of those 3 nodes is the fastest right now. And so it'll first send your read request to that client, to that node. If it doesn't come back in the average expected time for that node, it can just go ahead and send another read request to one of those other 2 nodes and say, hey, do you have this data, and can you tell me faster than this other slow guy which is not returned to me yet? And that way it will, or it can just shotgun a read request to all of your replicas all at once and return whatever comes back quickest to the client. So all of this is something else that you can take into account, the requirements for your application for how fast you want reads to be able to happen, what level of consistency you need to ensure that you're always getting the most up-to-date data from all of your replicas, all sorts of stuff like that. Also, 10% of the time, your read will create a read repair, which means that even if you had only requested a consistency level of 1, which means that only one other replica needs to be contacted for your read, in the background, that coordinator will still send a read request to all of your other replicas of that piece of data and try to confirm that it has the most up-to-date version. If it doesn't, then it will, again, asynchronously update that out-of-date node so that your data remains consistent across the cluster. You can also tune that up and down. If you have a low read rate, then maybe you want to turn it up. If you have a high read rate, then maybe 1% will be just as effective. Speaking of consistency level, there are several different levels even beyond this, but for read operations, one and any are the same. It will just return any replica, the first one that it's able to get a response from. Quorum in both cases means that it's one more than half of your cluster, or one more than half of the replicas for that data. So if you have a cluster of 6, but a replication factor of 3, then quorum will require 2 of them to respond. To positively respond, that is. All, in both cases, is all replicas. And with the case, in the case of writes, if you have a write of any, that means that if you connect to a coordinator and it's not able to connect to any of the replicas for that row key along the ring, then it will still return positive to your client that, yes, this has been written, if it was able to at least record a hinted handoff on the coordinator. So that means that the only embodiment of your data is a little notation in the system keyspace that says, yeah, when this node comes back up, I'll tell him to write this for you. Again, the consistency level for all operations is specified per request by the client. So you can do all sorts of things based on what your level of caring about that data is and how you're going to be reading and writing it. So, for example, you can always be consistent. So like this is where Cassandra violates the CAP theorem a little bit. You can still have always consistent access to your data, reading and writing it. If, for example, you write at quorum so that you always have a majority of your nodes have the data, and if you are reading at quorum too. Also, if you write at 1, for example, and you read at all of them, so if you have a lot of writes but only a few reads, then you can write to any of the nodes, and then whenever on the rare occasion that you need to read it, you check all of them to make sure you have the most up to date. Or vice versa, if you write to all of them and then you read only from one of them if you have a high read rate on your application. And also for rack and data center aware topologies, there are local versions of all of these. So you can, instead of writing at quorum, you can write at local quorum so that only your local cluster nodes have to confirm an operation. So speaking of reading, this is that same diagram here. The read operation, whenever it hits a given node to, a coordinator tells a node, please give me this data or whatever, it's going to look in its mem table, and then it's also going to look in all of its SS tables that apply for that piece of data. So it's going to, both times it's going to look in both of these data structures because mem tables have not been written to disk yet. That data only exists either in the commit log or in memory right there in the mem table. So reads will come from the mem table because it's faster. And then whenever you need to hit an SS table, this is the various steps of the data structures in Cassandra that it will touch. So not pictured in this diagram is a row cache, which is an on-disk optional data structure, which is essentially a list of all the different most recently accessed rows that Cassandra has seen on that node. And if it finds a hit in the row cache, it will immediately just return that and stop, and it won't do the rest of this. But that's the only short circuit in this entire system. And it's also very common to put that row cache on either like a TempFS or SSDs or something really fast, if you can. So in the Bloom filter, which we mentioned before, it's a funny name for a data structure which gives you a chance of knowing which SS table your data is on. So like I said before, there's going to be lots of SS tables, and in this entire process we have to do for each of them that our data is possibly on to make sure that we get the most up-to-date version of that row. So the Bloom filter will say that it does exist, in which case it's definitely sure, or it may exist in this particular SS table. And so in either case, it has to follow the rest of this topology to find out. So for each SS table that the Bloom filter tells the node to look at, it will first look in a partition key cache, which says that this row is in this SS table at this exact location in the table. So it can seek directly to that location in the file. If it's not in the key cache, then it will hit a partition summary, which is also in memory. And that's just like saying that this entire range of row keys exists starting at this position in your SS table. So it's not an exact index, but it points to the general location. And then from there, it can look at the exact partition index in the SS table on disk and find the exact row key that you're looking for. And if you're using compression for your SS tables, there's also another data structure in memory that helps it find where in the compressed data stream to look for a piece of uncompressed data. That's a newer feature in Cassandra. And then eventually, all of that leads to finding the exact data in the data portion of your SS table. Whenever you, if your Bloom filter points to something that didn't end up existing, you checked out an SS table because your Bloom filter told you to, and it wasn't there, it will update that so it doesn't go check it again. And then also, whenever you are writing something, which I didn't mention before, it will update that row cache. So if you make an update or delete to a row that was in the row cache, it will just remove it from that cache and let it get recached again whenever next time you read it. So as I said, the request from the client initially comes into the coordinator, and it decides which other nodes it needs to contact based on the consistency level. Internally, oh, actually, you know what? This slide was supposed to be deleted. Sorry. So compaction is what happens to your SS tables in the background, and it's part of like normal operation of your cluster. You don't have to tell it to do it. It will automatically do it based on different strategies that we're going to talk about in a moment. But whenever compaction is the only time that those SS tables are changed, because it's the process of taking multiple SS tables and putting them into one. And then after it's done that and verified it, then it will delete the old SS tables. And that's the only time that space is ever reclaimed on your server. So SS tables, as the name implies, are already sorted. So everything, whenever it's compacting a pair of SS tables or more than one SS table, it doesn't have to go back and forth seeking on them. Again, like everything else in Cassandra, it's all designed to be able to do sequential I/O. It can read right through all the SS tables that it's compacting and write a new one sequentially and not have to cause a high seek rate on your spinning disks. And also, there's a lot of tunable parameters behind this that allow you to say only compact this often, or only during this time of day, or only if the load is this level, or only compact at this many megabytes per second. So the two main strategies for compaction. The first one is size tiered, which allows you to compact a fewer amount of tables at a time, which is usually faster. It will increase your read latency, though, and especially if you have heavily updated data, not heavily appended, but heavily updated, because your given row could end up being in most or all of your SS tables. So as time goes on and as your application, your cluster grows, your read operations may end up having to hit all 70 or all 300 of your SS tables or something like that, which is ridiculous. So this strategy is primarily preferred for something like time series data, where you're just always inserting or adding new rows. The other strategy is leveled, which means it creates multiple levels internally for your SS tables, and it guarantees that your given row will only ever exist either on level 0, the highest, most volatile row, or in one SS table for any of the other rows. So what it does is it has some threshold where it will say level, really? What happened this time? Okay. So at some given threshold, level 0 will be merged into a new single table at level 1. And then at some point, tables at level 1 will be merged into a single table at level 2, and so on and so forth. It creates more I/O because you're typically going to be combining more SS tables all at once into a single table. And also, this strategy alone will not give you any sort of advantage if you're only writing once, like time series data, because the advantage is that you read in fewer tables because it's compacted, more structured. But if you're only writing once, it doesn't make a difference. The reality, though, is that your compaction strategy will look like this, because if you have a lot of writes to your cluster, then you'll have a lot of things, a lot of SS tables, really small SS tables at level 0, and then a few levels below that, and you'll have to check all of them for every single read. That's not ideal, and that doesn't really buy you anything then for a heavy write cluster. So there's also a hybrid strategy, which allows you to combine the two things. So it will do the leveled compression or the leveled compaction, but at level 0, within level 0, it'll be doing tiered compaction. So it'll still be combining, 4 25 meg tables into a single 100 meg table at level 0, and then tiering them beneath that. This is what you'll normally be choosing for most operations. And lastly, in this section, there's lots of different things that Cassandra does internally to keep itself consistent. This is, again, violating its own cap theorem that those 10% of those reads triggering read repairs that will naturally, just in using your cluster and reading data, will keep it consistent. Also, it's advised that you'll regularly be running a repair operation at some interval. You'll at least have to do that for as long as your tombstones are allowed to live on. So whenever you create a tombstone to delete data, that tombstone has an expiration on it where it will ultimately, through compaction, just remove that tombstone and all of its data. But you have to be able to repair at least as often as that happens, or else you might have weird things happen, like your deleted rows reappearing. You can also, whenever you do a repair operation, you can also tell it to only do a local repair for your local data center nodes. So you can tell, for example, one node in your data center to do a full repair, so it will repair across the entire cluster, across all of your data centers, and be completely consistent with all of them. And then you tell all of your other nodes to do a local-only repair, so that it will be consistent with that one node that did the cross-data center repair and everything else. So you can limit cross-data center traffic that way. So, various problems. There's all sorts of things that can happen, especially with any sort of complex system. I won't claim to know all of them, and Cassandra is a very actively developed, actively changing system. The last time I looked at it before preparing this presentation was 2.0, and now Cassandra's up to 2.1, and a lot of the main problems I was looking at back then are solved now. So TLDR, keep up to date. But in general, a lot of your problems can be caused by things like network partitions. If you have one data center not able to talk to another, or one rack not able to talk to another, or something like that, that will cause nodes to, like this group of nodes, to think that everything else is out of the cluster, or vice versa, causing split brain situations even, where you have some nodes that are only able to talk to each other, and if you have clients that are still talking to both sides of this split brain situation, then you can eventually, if it's only lasting for a small amount of time, it really just means that you'll just have a whole bunch of hinted handoffs stored for everyone on all the other nodes. But if your consistency level, for example, is not tuned appropriately, then it can cause those clients to either not be able to read at all, or not be able to write at all, or for them to always just be getting stale data, because the only nodes they're able to talk to possibly only have old information, and the new information is on the other side of the network partition. So we've talked about lots of different things that Cassandra handles down, like totally down very well, but there are still things that you need to think about beyond just being completely down, because the more interesting failure scenarios and where things can get corrupted and bad performance and still take your application down is where you have like partial failures or network partitions and stuff like that. Or maybe you have IP tables accidentally blocking the gossip port on your cluster. Not that that has ever happened to us in production. After you get Cassandra back up and you have all the nodes gossiping and sharing information again, it will pretty quickly share the node state across all of your nodes in your cluster, and they'll all know that people are back up. Those hinted handouts that they were storing for any writes will start getting sent to whatever node they were intended for. Normal read and write operations can pretty much occur and resume immediately after your nodes come back into the cluster and are visible again in the gossip protocol. And those normal read repair operations that we talked about will also typically keep your data up to date. For the other 90% of your reads, even if you're reading at quorum or all, then that means that the coordinator will still be getting a copy of the data from other nodes, and if it will still see the most up to date, the best version of it from whatever node had it at the time. But if it sees bad versions of that data being returned from other nodes, it will issue a repair operation for that row to that node, asynchronously all on its own. So just having a cluster able to talk to itself and talk to each other is enough to eventually bring things back into working order. All of this, of course, incurs a performance hit because it has to do additional repairs, additional confirmations of your data. So you can initiate a repair whenever you want to essentially do all of this at your own request and your own control. But in a lot of cases, it's not necessary. In a dire situation, though, where you have like a complete total node failure, or you have corrupted data maybe, or maybe a server died in the middle of writing an SS table or something like that, and instead of trying to recover that node with what you've got, a lot of times it is easier to just delete everything on that node and reprovision it as if it's a new member of the cluster. And then, if you're using vnodes, it will pick up its whole list of partitions that it has and start syncing data from other replicas. And there's an entire bootstrapping process that Cassandra takes. It can go through to get data from all members of its topology, and eventually just bring itself back into working order. So it's very self-healing. Querying data out of Cassandra, I mentioned there's CQL. It looks a lot like SQL, it works a lot like SQL. You'll typically only be doing things keying off of your row key, so you'll always be using things like where your row keys equal blah. And even if you're using something else like the thrift protocol to talk to Cassandra, not CQL, which was only added in Cassandra 1.2, you'll still probably be using it to update the system key space, to update the metadata about how the cluster works or how your key spaces work and stuff like that. Nodetool is a tool that comes with Cassandra, which allows you to interact with your cluster as a whole or that given node that you're running it on. There's a few helpful things, or it does lots of things. It's essentially just a JMX client that talks to the Cassandra instance. But a few of the more frequently mentioned and useful subcommands that it has is CF histograms, which just shows you through the gossip protocol the latency for read and writes across your entire cluster as seen from that node that you're running it on. This is the data that is used by coordinators to know the optimum node to send a read to and stuff like that. It's also really useful to monitor the health of your cluster. TP stats shows you a list of all the different threads that are running. So there's all the different operations and things that Cassandra does internally to keep itself consistent, to do flushes to disk, to do compaction, to monitor other nodes, excuse me, and to be able to update other nodes if they come back up, are all in different threads, and you can monitor what those are all doing there. And then nodetool ring will show you that node's perspective of what it thinks the rest of the cluster looks like and what partitions are on each of those other nodes. And then, as I mentioned before, there's the system Keyspace, which is a lot like MySQL's performance schema database, and it has all sorts of column families within it that are useful to look at. A lot of times there's tools to look into the stuff for you, so you don't need to be splunking in there on your own. But the hints that are stored for hinted handoffs are inside there. There's a local column family which stores this particular node's state, and also a peers one which stores all of its remote states. And then all of your column families that you define on top of your data and all of your key spaces are all defined inside the system Keyspace. And I'm not sure if I'm over time or not, but that's all I've got for now. Any questions? Yes. We are using an ancient, old-ass version of Cassandra. 0.9? 1.0? 1.0, that's right, yeah. Yeah, so for Rackspace emails, anti-abuse outbound spam enforcement system, it stores counters of how much spam and ham and stuff like that that you have sent, and all of that, the policy that it enforces and those counters are all stored in Cassandra, and we're using the vendor's packaged version of Cassandra, which is 1.0. And at the time we were deploying it, we knew nothing about Cassandra, and the idea of upgrading or touching it ourselves was really, really scary, and that's why I was sent to training. Now it's probably not that big of a deal, but we also don't care anymore, I guess. But if we did, look at all the really cool stuff we could do. Let me see. Does anybody in video have any questions? Oh, I'm actually within an hour. Neat. Okay. Yes. So compatibility within versions is sort of a touchy subject. It is intended, at least, that you can do upgrades of a cluster in place. So if you have an entire cluster of 1.0 nodes, you can upgrade to 1.1, 1.2, or whatever, one node at a time, and eventually get your entire cluster up to the new version without having to even have downtime. Because if you're tuning everything else correctly, then you've got replication factors and consistency levels and stuff like that that ensure your operations can normally go on. That all being said, I guess as a personal engineering opinion on the project, Cassandra is relatively new. I don't know, when was it started? 2009 or something like that, and it has been undergoing major changes even between 1.1, 1.2, and so on. So those older versions have all sorts of known bugs and all sorts of problems, and then compact that on top of trying to get something like hinted handoffs or gossip protocols or whatever working between incompatible versions might be asking for trouble, and it might be easier just to stand up a new cluster side by side and migrate your data. Those SS tables, for example, actually, there are tools to dump your SS table to JSON and then dump your JSON into an SS table. And so you can even just use something it sounds janky, but you can use something like that even to migrate to a new version of a completely different cluster. Everybody excited about Cassandra? I've just been waiting for my own, I learned all of this from going to a class and being immersed in it for a week, but I'm just waiting to have some sort of personal project that I want to use this for, because like the next major personal project I have, I will be doing it in Cassandra because it sounds really fun, but nothing's come up yet in the last year. We have 3 distinct and isolated clusters across 3 regions. 2 of them are 3 nodes each, and the other one is 6. The original design was to have them all shared, multi-data center and stuff like that. But after being this close to production deployment with that and realizing that, gee, this isn't working, and it's not actually able to write anything to any of them and run any repairs, then we panicked and backpedaled. Okay. Let me know if you have any questions.